Video we left off talking about sequence parallelism and tensor parallelism. Now let's jump into context and expert parallelism, which help us shard activations. Context parallelism by splitting up the sequence in our attention calculation, and then we use ring attention to synchronize and communicate between the GPUs to essentially transport the attention scores between the graphic processing units. And in expert parallelism, because the token is not fed through the entire feed-forward neural network, then simply the activations are less, because when you pass a input through a smaller model, then it will have less activations because there's less model weights, which you would need to store activations for. So as I've just stated, context parallelism targets the challenge of training with very long sequences by sharding along the sequence dimension. And while most operations like MLPs and layer can process sharded sequences independently, attention layers require communication since each token needs access to the key values from the full sequence. This is handled efficiently through ring attention patterns that overlap computation and communication, and context parallelism is particularly valuable when scaling to extreme sequence lengths, that is to say, beyond 128,000 tokens, which nowadays is commonplace, where even when using full activation recomputation, which is to say we do not store any activations and recompute them during the backward pass, in essence doing 2 forward passes per backward pass, even when this is done, the memory requirements for attention are prohibitive on a single GPU with such a sequence length. And for context parallelism, we have the exact same diagram that we looked at last video. However, the domain has changed and we do context parallelism within the multi-head self-attention layers inside of our transformer block, and anything else here, if you'd like to have the explanation for and you have not watched the last video, then please do. Now, when it comes to expert parallelism, we dynamically route tokens to relevant experts in communication, with the key operation being all to all. This is the distributed communication primitive used in expert parallelism, which routes tokens once again to their assigned experts and then gathers the results back. While this operation introduces some communication overhead, it enables scaling model capacity significantly, since each token is only processed during inference and training by a much smaller fraction of the total parameters. And in terms of distributed training/inference, partitioning experts across GPUs becomes relevant when models scale to a large number of experts, which in the case of DeepSeek v3 was 256. And we have our transformer block where we can see that there is an all-to-all operation at the beginning and end, where we are routing the tokens to their respective experts and then routing them back for the layer norm. And this is only in the feed-forward neural network, of course, since there's no such concept for experts in multi-head self-attention, or at least it has not been invented yet. Moving on, the similarity between expert parallelism and data parallelism in terms of input handling, which is to say that we're splitting the input across, in the case of data parallelism, GPUs, in the case of expert parallelism, different feed-forward neural networks, which is why some implementations consider expert parallelism to be a subset of data parallelism, with the key difference being that EP uses specialized expert routing rather than having all GPUs process inputs through identical model copies in the case of data parallelism. And now, in summary, we'll have some commentary on all of the methods that we've learned so far. So tensor parallelism and sequence parallelism affect computation throughout the entire model by sharding both weights and activations, and this is to say when they are combined. Context parallelism primarily solely impacts attention layers, since that's where cross-sequence communication is required, while other layers operating independently on sharded sequences. So this is the particularity of context parallelism, where despite sharding on sequences, we still need to maintain the communication between the devices so that they can communicate their attention scores. And then expert parallelism is affecting only the MOE layer, which replaced the standard MLP blocks used in just the vanilla transformer, and does not affect attention or any other component of the transformer block. And pipeline parallelism, in addition to the zero redundancy optimizer, are not specific to any submodule or component of the transformer, with the exception that modules and layers need to be balanced in pipeline parallelism, which is to say that the first and last layers are treated differently because of their additional embedding layers. So when you have the input to the transformer model, you must embed along the vocabulary size, and then you also have the last embedding layer, which gives you the logits, which are then soft maxed over in order to perform the next token prediction. And then here we have a table that compares the four of the 5D dimensional primitives, or rather communication optimization strategies. So when it comes to tensor and sequence parallel, I mean, this is kind of just repeating what was said here, I guess in a more structured format. We have sharding activations along hidden and sequence dimension, whereas context parallel is along the sequence dimension. I mean, not whereas, context parallel and sequence parallel are the same sharding dimension, but it's in a different component, whereas context parallel is in the layer norm and dropout if it's implemented. Sequence parallelism is on the layer norm and dropout, and context parallelism is in the attention. Expert parallel is just along the feed-forward neural network. And if you'd like to go through the remaining items in the table, then please pause. But for the sake of time, I'm going to skip to summarizing it all. And this is done in this diagram, which includes all 5 of the parallelism paradigms that we've discussed up to now, with mixture of experts, of course, to enable expert parallelism. I'm not brave enough to go through a single pass of the network and work out through all the dimensions and understand all of the communication happening. But if you are, then I commend you. So you could try to go through this and battle with Claude or ChatGPT to understand each component. This will give you a very deep understanding, I can guarantee you. And there's also these graphs here that represent side by side a full overview of the memory savings for each of these strategies. And they've plotted them with different sequence lengths and selective gradient checkpointing and full gradient recomputation on the bottom. So this is why in the bottom you see that the activations are 0, because we're recomputing them completely. For some reason, there is some activations for no parallelism, or actually all of them. Maybe there's some activation that you just cannot. Well, I guess that's the output. Yeah, like in terms of the output activation, which is just the last activation, if you discard it, then you have to do the forward pass again. So you do have to cache that for sure. And we can see that when you do have full activation recomputation, you're able to fit much larger models, but this is at the cost of more computation. I think it was a 40% increase in computation. In any case, we have all of the parallelism techniques that we've discussed in this example. One thing that's interesting here is that context parallelism doesn't make that much of a difference from no parallelism. And just as a reminder, context parallelism is the method that splits up the attention head. And perhaps this is because we're only going up to 16,000 sequence length or context length size, which is much less than the 128K that they discussed, where context parallelism becomes necessary. And then another high-level review of everything we've discussed so far. So data parallelism is saving memory on the activations by reducing local batch size. The sharding dimension is the batch, and the disadvantage is that we cannot infinitely scale it, because then it will increase our max batch size, which is usually optimized to lead in a positive training direction, which is to say, like, improve the training dynamics. And then pipeline parallelism is for the parameters. We split along the model layers. And the disadvantage is we do have idle time. TP/SP is parameters and activations, which are sharded. And this is done along the hidden dimension for tensor parallelism and the sequence length for sequence parallelism. And it requires high bandwidth communication, which means it should be within the node. Once again, if you want to read the rest, then please go ahead. There is quite a lot of similarity between this table and the other one, so I don't want to repeat myself. And another note that the authors have put here is that there's no silver bullet for magical scaling, and we have to combine them in one way or another. And now we're going to talk about what type of methods and heuristics you can use to combine our different parallelism techniques. So to find the best training configuration, we have a 3-step process, if I'm not mistaken here. So let's read what they have to say. And the first step is split up into a GPU rich and GPU poor case. And this is just to say how many GPUs that do we have, because if you don't know how many devices you're training with, then it's kind of hard to get your hyperparameters set up. So if you have many GPUs, then for a model under 10 parameters, it's possible just to do a single parallelism technique on one node, such as zero latency optimizer 3, tensor parallelism, or I guess combined with data parallelism. And this is using full activation recomputation to reduce the activations and on one node. Then for 10 to 100 billion parameter models requiring more than 8 GPUs, there are several options: tensor parallelism up to 8 GPUs, so within the node, with pipeline parallelism, in addition to TP with zero latency optimizer 3. In I think 2 videos ago, we discussed the similarities with pipeline parallelism and the zero latency optimizer, which make it such that they are not really combinable, at least not 0.3 with pipeline parallelism. And thirdly, they say you can also only use 0.3 or purely data parallelism, but this contradicts what they say here, where you should use a single parallelism technique with up to 10 billion and then more than one parallelism technique from 10 to 100 billion parameter models. And then they kind of switch up the theme here. They're saying that if you surpass 512 GPUs, then pure DP/03 will start to become inefficient due to communication costs. And then it can be better to combine DP with either TP or PP. A lot of acronyms here. And then if you surpass 1024 GPUs, then a recommended setup can be tensor parallelism for each node with data parallelism and zero latency optimizer 2 with the pipeline parallelism. So once again, when we said that pipeline parallelism does not go hand in hand with the zero redundancy optimizer 3 due to the weight recomputation required, or rather recommunication required at every single layer of the forward pass with zero redundancy optimizer 3, which if we shard along the layers in a pipeline makes it much more communication intense, then we don't combine those two methods together. Instead, we just use zero redundancy optimizer 2 in order to maintain the weights. So we shard the optimizers and the gradients, but not the weights themselves. Some special considerations is that if you have very long sequences, use context parallelism, and if you're using mixture of experts, use expert parallelism. They're definitely a bit obvious in this playbook with certain recommendations, but gotta read them just in case, I guess. And then when there's a GPU low regime, you can increase gradient accumulation because that does not require increasing GPUs. You're just kind of reducing the level of parallelization. And you can also enable full activation recomputation, which is kind of like free lunch for memory savings. Or not, it's not free lunch at all, but you're getting memory savings at the cost of compute. Okay, now step 2 is regarding the global batch size. So if you have, once you get your global batch size, and once again, this is kind of a empirical value, such as like 1 million tokens per training step, which is something you can find online and just choose as the parameter, which will likely be scaled up, at least, for example, in DeepSeek R1 and V3, if I'm not mistaken, the global batch size increases as the training run progresses. But anyways, if you want to increase the current global batch size, you can just simply scale up data parallelism or gradient accumulation steps. So just run more batches per training step and then average over those batches when you use the gradients to update the weights. And we can also just use context parallelism to split up the sequence in the multi-head self-attention layer. And it's just the opposite of that if you want to decrease our global batch size. Now, for step 3, in terms of optimizing training throughput, there are a few tips, which one that I've mentioned time and time again is use intra-node tensor parallelism, which is to say don't exceed a node size of 8, or rather don't exceed 8 GPUs if it's an NVIDIA rig for a tensor parallelism setup, because beyond that, the inter-node communication overhead is quite overbearing. In essence, it suppresses the benefits gained, and I'll show this in a graph at the very end of today's video. Another option is to increase data parallelism with 0.3 while keeping the target batch size. So I imagine that if we increase our data parallelism, we'll have to decrease the size of our batches. And once again, this is more of a technique that is available in a GPU-rich regime. And when data parallelism starts to become a bottleneck, we transition to pipeline parallelism. So pipeline parallelism is definitely one of the techniques which scales well into the 512, 1024 GPU training runs. And just another advice is just try different parallelisms one by one, kind of like a science to it. You just have to make experiments, and then try several micro batch sizes to aim for an optimal balance between max, global batch size, model size, compute, and computation. And now I think this is the last thing that I'll discuss, or no, there's a bit of section left. So they had a graph here which shows the benchmarks that they did across thousands of configurations, which are on 8 by 8 H100 setups with up to 64 nodes. And they used a sequence like the 4096 with a global batch size of 1 million tokens per training step. And in this case, yellow means it's using a high MFU, so like the GPUs are being used properly and in a efficient manner. And then this is seen through the color. So the brighter the color, the higher the MFU, which is good. And you can also just find the raw number itself. So for example, 5.25, this is I think the worst result in this graph, is way at the bottom. And then the gigabyte value is the amount of memory used by each GPU. I think on average, I forget, it's either on average or the max memory per GPU, one of these two in the training run. And lastly, we have the model size. So they do from 1 to 80 billion parameter models and from 1 to 64 nodes, as they have stated right here. And like I mentioned, once we are at 8 nodes, we're in a pretty memory and communication efficient situation. And then as soon as you jump to, whereas it should like decrease, like you can see here, it decreases all the way to 8, but whereas it should continue decreasing because of the communication overhead and other inter-node communication bottlenecks, which I do not know of, the memory bottleneck actually just doubles in most of the situations. Or in this case, I guess it does not double. It's more of a small addition. And I just realized that as the model size becomes bigger, then it actually does start to decrease, which is interesting. But anyways, if you have a small model, then if you surpass 1 node, then you don't know what you're doing, I guess. And then in the right graph here, we have all of the configurations with the data parallelism amount, the tensor parallelism, etc. So you can see, for example, for not all, but for 3 of the 64 node setups, we had a data parallelism of 128 with a GAS. I'm not sure what the GS is, so if anybody knows, please tell me, and a minimum batch size of 2. So 128 times 2 gives us 256. And this, I think, means that there are 4 GPUs per node. So this is worth noting. I think they have 8 GPUs per node, meaning that there are 512 GPUs and we only have 128 GPUs in the data parallel regime. So I guess this means that each GPU is doing 4 micro batches, because 4 times 120 is 512, but it's giving micro batch sizes 2. So I'm not entirely sure if there's a typo here or if I have a misunderstanding, but once again, if somebody in the comments knows, that would be very helpful. So some high-level observations that they've put themselves is that as you increase the number of nodes, we observe a decrease in efficiency. So essentially, as you go up, the colors become darker. This effect is particularly pronounced for smaller models, which have a lower compute to model size ratio. So I guess the reason why we have such a pronounced drop in efficiency for the lower size models as we go from 8 to 16 nodes is because of this small compute to size ratio. So the GPUs, I suppose, are not able to get full utilization of the compute capacity. And then second thing worth noting is that larger models present a different challenge, which is to say that the memory requirements grow substantially, of course, since the models are larger. And there are 2 situations, one being the model doesn't fit at all, or it barely fits and runs inefficiently. So this is the case when we have a 80 billion parameter model that just barely fits on 4 nodes, which would be 32 GPUs. And in this case, we have a really high amount of memory being used per GPU, the highest of the entire batch, if I'm not mistaken, 65. Oh, never mind, there's a higher one here, 66. And these are 80 gigabyte VRAM GPUs, so that's worth noting. And we also have a really low value for the MFU at 14.76. And let's look at some lessons learned that were taken away by the team during the training runs which they conducted to get this graph up above. One was that PyTorch processes sometimes fail to clean up properly. The Slurm job manager, which I think is what is scheduling all of the jobs, forcibly terminates some, leading to node failures. That simple benchmarks that should take minutes stretch to hours. Some jobs just never get completed. And they ended up spending a significant amount of time on things like minimizing cluster restart times and optimizing idle times, analyzing detailed NCCL debug logs, which is the communication protocol in NVIDIA, understanding memory usage patterns and CUDA memory allocator behaviors, improving pipeline parallelism performance on multi-node setups. These challenges deserve their own story, blah, 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 blah. Reproducing theoretical results is challenging in practice, but they do have these open source repos, which try to make this a open practice and not a weird esoteric science. And this concludes the deep dive into the distribution methods of 5D parallelism. Taking a step back, our discussion so far has often relied on critical assumptions such that communication and computation can be efficiently overlapped on GPUs without any impact on the computation throughput. And this is more nuanced in reality, because when using common communication primitives like NCCL, send/receive, etc., we face hidden contentions between computation and communication resources, as communication kernels usually make use of the same GPU SM, which are string multiprocessors, as used for computation, leading to decreased throughput when computation and communication are overlapped. And to truly optimize our distributed training, we need to go into the deeper GPU architecture itself, which is CUDA. Something to note here is that if you want to look at a blog discussing synchronization of computation and communication by the PyTorch team, then please check this out. Otherwise, we'll see you in the next video discussing CUDA.